All right. So, welcome everyone. I'm glad that you are here in person. This is our second in-person seminar in 2 years, I would say. So we are really glad to have Professor Tariq Syed from the University of British Columbia. When you come our age, the bios become so large. So I'm not going to read all his bio. Most of you know him very well from his research, his papers. He's a Canada chair professor and all kinds of awards. And his main area is traffic safety and intelligent transportation systems applied to that. There's, I was reading here more than 250 papers, but now probably more since this was written. So we're really glad to have you here, Tariq. And I'm glad that you could make the fly from British Columbia. It's a long flight, but now you're all flying. And as I said, most of the students are here interested in traffic safety and Zoom also. So we're really looking forward to your talk. And hopefully students will be a little bit more engaged than they're in my classes during this COVID, and they'll ask questions. And we'll be having a great presentation. Again,
thank you very much.
Welcome, Professor Syed.
Thank you. This is my first business trip since 2 years. So I'm really glad that I'm traveling again. I used to travel every month, at least once, not in the last 2 years. So my presentation today is about real-time proactive road safety management techniques. And this is an outline of my presentation. I'm going to just give a brief background about road safety and why it is important, which I'm sure most of you will know that already. And then I'm going to talk about new trends and opportunities on road safety analysis. I'm going to talk about smart mobility and big data, real-time safety management, and I will be giving examples and case studies from some of the work we're doing in this area worldwide. So as you all know, the importance of reducing the social and economic costs associated with road safety cannot be overstated. We have about 1.35 million people killed every year. And for each one of these fatalities, we have 40 injuries. That's worldwide, every year. In Canada, the annual cost of road collisions to the Canadian economy is estimated at $62 billion. So can you think of any other profession that has a product, and our product is a road system? And this product is associated with 1.35 million fatalities. And we are getting away with it, usually by blaming the road user of the system. So we're creating a system and we're telling that it is not working very well. It has all of these fatalities because people do not know how to use our system, which is not really fair. But this is a hidden epidemic. Doesn't really make the news. And in my opinion, this is for three main reasons. These fatalities occur 1 or 2 at a time. It's not like an airplane crashing, killing 400 people one time a year. These fatalities usually are 1 or 2 at a time. 9 out of the 10 fatalities occur in less developed countries, not in the West and North America. But the third one is really important. There is a feeling that these are just accidents. They cannot be predicted and prevented. They are a fact of life, which is not true. They can be predicted and they can be prevented. So the good news is that there has been significant advances made over the last decades in road safety. We have about 50% reduction in fatalities, despite an increase in traffic volume and mobility. We have done a lot of research and we made a lot of advances. And these advances are creating a movement towards explicit consideration of safety in transportation planning, design, and management. So this is the good news. However, we have also some problems that we need to take care of. So despite these recent advances, there are challenges that are complicating the future direction of road safety. And those of you who are familiar with fatality rates, in recent years, the fatality rate curve has flattened. And in many countries, it is starting to increase. So all these significant reductions that we received in the past are not continuing. And these challenges, in my opinion, again, include these 4 main points. Most of the traditional research on road safety focuses on the statistical techniques to model collisions. We don't understand very well. Less attention has been devoted to improving our understanding of collision factors and how safety measures work. We just use police reports, numbers of accidents to fit a regression model and say, we're going to use this regression model to identify black spots and treat them and all of that. Reliance on collision data is reactive, and it has fundamental ethical and practical issues. This is extremely important. It has a fundamental ethical issue. To identify a location as having a safety issue, we need to observe collisions first. So to prevent fatalities, we need to observe fatalities first. People should die first before we intervene to make a location safe. Doesn't make a lot of sense. Collisions represent a situation in which the road system has failed. Yet, our understanding of this failure mechanism is poor, which reduces the accuracy of the diagnosis and remedy process. It is time to use more realistic, proactive approach to improve road safety. So what are the new trends in road safety analysis? So I'm going to list all of them, but I'm going to focus on the last 4 items. Explicit evaluation of safety impacts. Safety used to be an implicit evaluation based on expert knowledge and expert opinion. But now it is explicit, separate evaluation from any other thing like travel time and delay and mobility. We are quantifying that. We have the ability to estimate the number of collisions associated with a specific design or a change in a specific design. We are moving away from rigid standards and warrants. It is not either we meet the warrants or the standards or not. It's now flexible. We can make a specific design safer by doing some changes. It is not yes or no. We are going proactive. We are not waiting for collisions to happen before we intervene. We are using safety surveys. And in my opinion, this is one of the most important advances that took place in road safety analysis. That we're not using collisions anymore. We're using safety surveys such as traffic conflicts. We are including road user behavior in our safety analysis, which we couldn't do before because we didn't have the technology to do it. And we are very excited about the new era of smart mobility and big data, which will allow me for the first time to do real-time safety optimization, something that we couldn't do before. I'm going to focus, I'm going to give you examples of some of these 4 points at the end. Let's talk about proactive road safety management. As I mentioned, the traditional safety analysis is a reactive approach based on historical collision data. But collisions are rare and random events. So we need to wait for about 3 to 4 years to collect an adequate sample of collisions that we can statistically analyze to get some output. Not only that, the collision data itself has many, many problems everywhere. In Canada, in the US, in Europe, we always have problems with the accuracy and reliability of collision data. It takes a long time. Collision data doesn't offer a good understanding of how safety countermeasures work and how the failure mechanism of the collision took place. So stated bluntly, as I said, fatalities and injuries need to occur to justify investment to reduce future collisions. that's the reactive approach with some unethical issues, in my opinion. We need a more proactive approach, and this is where we go to surveys. So we started working on this traffic conflicts. Started in Europe, actually, in 1980 or something, where people said, let's use near misses or traffic conflicts. And this is a very famous safety pyramid that many of you are familiar with. And they said, if we rank all interactions on this scale, you will find fatalities and injuries at the very top, followed by near misses, serious conflicts, less serious conflicts, and then undisturbed interactions. But actually, this didn't go anywhere. There was a lot of hype about using conflicts in 1980 or something, but it didn't go anywhere. Because the cost of collecting this conflict data was very high, was done manually, and the reliability of the manual observers was very low. Until in about 2005 at UBC, my university, we decided we can automate this process using video analytics. So we started working in 2005. We had our first system that's capable of detecting near misses automatically in videos in 2006. It was like 16 years ago. Now, there are many companies and many researchers are using automated computer vision techniques to analyze near misses. This is an example of the system that was developed in 2006. You can see this is downtown Vancouver. You can see an interaction. It is in slow, so this is not the real speed of the video. But you get a lot of details. You can see on the top left the deceleration rate. So the van reduces speed or decelerated by 4 meters per second square to avoid hitting this pedestrian. On the bottom left, you see the time to collision. It's about 1.5 seconds. We were about 1.5 seconds away from a collision. And on the right, you see the vehicle speed and the pedestrian speed. And the pedestrian speed profile is fluctuating because pedestrians are taking steps. So with each step, there is a fluctuation. And actually, we can use this speed profile to classify road users with very high accuracy, just from the speed profile without looking at the shape. It works well, even in congested area. This is Shanghai in China. And you can see that we can track very well. And we get very detailed information. For example, we get the yaw rate, we get the acceleration, deceleration, and many, many things. This is some work we've done with the New York City DOT. I think that was maybe 5-6 years ago. That's downtown. And we were able to diagnose an intersection, getting traffic conflicts, getting heat maps, making it changes, and correcting the location. This is downtown Vancouver, where they are very big on bike facilities. We are converting many vehicle lanes to bike lanes, and we're doing a lot of detailed behavior evaluation of these near misses to prevent them. And we can analyze collisions. So this is in one of the cities in British Columbia, where they send us their videos, we analyze the videos, and we can get a lot of detailed information. We can get whether the signal indication was green, yellow, or red automatically. We can get information about the deceleration rate, whether the driver took an evasive action, and many, many details that can help investigate the collision and why it took place. We can use it for diagnostics. So this is the highest collision prone location in the city of Edmonton. And again, we get video data, we do an analysis, we produce all of these heat maps where the problems area are, and we get countermeasures, we implement them. And this location, for example, did not see a collision following the treatments that were implemented for the last 5 years. And we can do before and after evaluation, which is a big application in road safety. We want to know whether the investment we make in improving road safety is working or not. With collision data, we need to collect about 3 to 4 years of collisions before, 3 and 4 years of collision after, to do a proper statistical and analysis. We produce all of these heat maps where the problems area are, and we get countermeasures, we implement them. And this location, for example, did not see a collision following the treatments that were implemented for the last 5 years. And we can do before and after evaluation, which is a big application in road safety. We want to know whether the investment we make in improving road safety is working or not. With collision data, we need to collect about 3 to 4 years of collisions before, 3 and 4 years of collision after, to do a proper statistical analysis. Not only that, we are interested in seeing collisions, so our evaluation would work. We are interested in seeing events that we're trying to prevent in the first place for a proper evaluation, which again doesn't make a lot of sense. Severe and conflict. This is from Vancouver, where they introduce a lot of what they call LPIs, lead pedestrian interval. It's becoming very popular. And you can see the frustration of pedestrians crossing the street. And with LPIs, it is very, very cost effective. Just a small change in the traffic control, and you get significant reduction. You get about 20% reduction, depending on the volume. So this 20% can go up to 30, 40% under specific circumstances. This is one of the most important locations in the city of Vancouver. It's called the Burrard Bridge, where they had many, many conflicts between vehicles and cyclists going on the bridge. What we did is that we closed this right-hand ramp and brought all the vehicles to a signal here. So this was closed. We brought all the vehicles here. And again, you can see immediate. We did the video analysis. We made all the geometric design changes. And you can see what happened to a reduction in near misses. Huge reductions by making the changes following an analysis of few days as opposed to few years. We are also now getting better understanding of how road user behavior affects safety. Get very detailed microscopic information. You can see the steps. Each one of these fluctuations in the speed profile is a step taken by the pedestrian. We can get the step frequency, the step length. We can get the stability of the walking mechanism. We get very detailed information. This is a pedestrian speed profile, a cyclist speed profile, and a vehicle, which is linear. And we can reconstruct the signal. So you have, I think, the original is the blue, the reconstructed one is the red, and we get the dominant frequency of the signal, which will be the step frequency of the pedestrian distance. And this will be the cadence of the cyclist profile. So you get very detailed information, and we can use that in classification. So we're getting about 85 to 96% correct classification rate, not from the shape of the object, but from the walking mechanism or the speed profile. We can point to a specific pedestrian, and for example, you're going to see this pedestrian. He will stop to talk to his companion. He sees a drop in speed, and then they walk together. You get very detailed information about why things are taking place. This is crossing speed in downtown Vancouver. A lot of jaywalking, people crossing from main block. And you can see that pedestrians crossing on the crosswalks are much slower than these violating pedestrians. This shows you how the speed crossing changes according to what phase you are in. You can see that violating pedestrians are really running at 2.6 meters per second compared to about 1.3 for pedestrians crossing on the walking phase. As I mentioned, we can analyze the signal, apply all of these pattern recognition techniques. We get the step frequency, and we can get the step length from walking speed equal frequency by length. And we can use that in many things. In this case, for example, we can classify gender by looking at the different walking mechanisms. Of course, it will never be accurate, but you get about 85% accuracy. Just looking at the walking mechanism of the pedestrian without looking at the shape. We can automatically identify evasive actions. You can see the pedestrian will start running, and here you will see the change in the step frequency. We can apply again some statistical techniques, permutation entropy, for example, and you can see the change in the entropy. And this value can give you a very good indication of the strength of the evasive action, which can also be used as a traffic conflict indicator. This is some work that we've done in Vancouver to try to automatically identify pedestrians who are distracted while walking. Again, without looking at the shape, we're just looking at the walking mechanism and the change, the dynamics of the walking mechanism. And we get about 80% accuracy because the walking mechanism is quite different than pedestrians who are not distracted. We can tell whether pedestrians are walking in groups or individually by, again, matching their gait parameters and speed profile and things like that. This is, for example, this is at UBC, Cyclist Speed. And you can see that cyclists who are using the sidewalks are much slower than cyclists who are using the regular lanes, and cyclists in the inside lanes are faster. Usually they are the more experienced cyclists. You can tell whether a cyclist is wearing a helmet or not. You can point to the head, and from the head, you can tell whether there is a helmet or not. It's difficult to collect this data manually, and in this case, we got about 85% accuracy. We can model pedestrian movements using AI techniques. So we introduce these interactions to an algorithm, inverse reinforcement learning, and we can duplicate how road users are interacting. So when we develop simulation models, we can duplicate the actual behavior of road users in interaction, including conflicts and near misses. We can simulate them with actual behavior of road users. This is an example from Vancouver. They have a big event in the summer, fireworks, where they close the downtown to vehicles. And in this case, one vehicle, one big van entered the crowd, and it shouldn't be there. And we tried to use our model to mimic how the group of 6 pedestrians here will respond to the presence of this van. And you can see this is the actual trajectory versus the simulated trajectory. And the shape looks not bad at all. How they interacted in speed profile to the presence of this van in the crowd. The last thing I want to talk about is smart mobility, big data, and real-time safety evaluation. So I'm very excited about this area. We are on the cusp of a new era of smart mobility. The application of information and communication technologies will make a huge change in the way we do business, designing, operating, and managing our road facilities. Autonomous vehicles are expected to provide considerable social and economic benefits. There are still some issues because they haven't been evaluated very well, but we're expecting significant benefits. But in my opinion, This is the most exciting part of the equation, the big data that will be generated. This big data coming from autonomous and connected vehicles will allow us to optimize the transportation network for road safety in real time, which we couldn't do before. So road safety engineers, when they talk to the traffic engineers, we were always in a disadvantage because we are using collision data. They have a measure of vehicle delay that they can get every cycle or every 5 minutes, and they can optimize their system for vehicle delay. They can coordinate signals, they can do many things. We couldn't do that because we couldn't measure safety in real time. Now, with all of this big data, including vehicle trajectories, this will give us a chance of optimizing the network. So this would be a methodology that departs fundamentally from the past 50 years of reactive safety management based on population data. The real-time safety optimization, and there will be different examples. We are relying on safety surrogates. We're not using collisions anymore in real time. We're getting vehicle trajectories. And we don't care where the vehicle trajectories are coming from. They can come from cameras, they can come from LiDAR, they can come from the connected and autonomous vehicles. Any source of information for us is active. And now there is significant advantage in the technology of edge computing. There are many cameras now that can get these trajectories in real time at the intersection. So while they are collecting the video, they can give you the trajectories in real time. And real time doesn't have to be exact, even few seconds late or something is still okay. So this is an example from some work we're doing in Vancouver, where we're using edge cameras to get the videos, and from the videos we get the vehicle trajectories. And these vehicle trajectories can give me a lot of detailed information. So in this case, we can get things like shockwave area, shockwave speed, many dynamic traffic parameters in real time that we didn't have before. We take these dynamic traffic parameters and the vehicle trajectories, we use them to get conflicts and near misses in real time. And we have techniques, statistical techniques, to model these near misses and convert them to crash risk, real-time crash risk. So this is a technique called extreme value distribution. So we take the extremes of the traffic conflicts occurring in different time intervals, we fit a distribution to the extremes, and the tail of this distribution is our crash risk. And it works very well. So these are the near misses occurring. We take the extremes, the ones in red, we fit this distribution to the extremes, and this is the negated conflict indicator. So a 0 means a collision. So this tail area is a very good indication of actual crash risk. And you can see that we can aggregate this small time interval crash risk to predict collisions per year. So these are 4 intersections in British Columbia. The green line is the actual collision frequency that took place. And these dots are our estimate of the collision over the 1 year, aggregating these small interval probabilities. So it works quite well. But what's really good, take this distribution and calculate real-time safety indicators. This will change, let's say, cycle by cycle. So we can get, you can see here a cycle. So this cycle has a high crash risk. And this is another measure that fluctuates more. And we can use that in the optimization of the transportation network. So one example, this is data from Greece, Athens. And you can see that we're using data from, so one example, this is data from Greece, Athens. And you can see that we're using data from vehicle trajectories, to come up with these heat maps in real time. So this changed in this case, 4 minutes, depending on the volume and all of that. And we can use these to do many, many applications. For example, if you use Google Maps, you get your best route from A to B based on travel time. I can tell you which route will be the safest route. And I can have a multi-objective optimization for safety and mobility. And the routes are not the same. Safest routes are not the most efficient routes from travel time point of view. They differ significantly. I can take these measures, the real-time measures, and use it to optimize signals. So adaptive traffic signal control has been there for some time. There are many cities applying this, including Vancouver. And they try to optimize average vehicle delay in real time. I can do the same thing for safety. So in this example, we are taking 2 cities in Vancouver, and we're training the system to minimize these real-time crash risks. And the system, this is the training, and you can see that after some time, it will learn the best way to manage the traffic control, and it will converge. And once we do that, this is the signal operation. This is the number of conflicts. This is before optimization. This is after optimization. We can get significant real-time safety benefits from these new techniques. And we couldn't do that 3-4 years ago because we didn't have the ability to measure road safety in real time. The last thing I want to say is how we handle the conflict between mobility and safety. This is a very big issue. In general, road transportation involves the consideration of 2 main values: mobility and safety. There are other things like environment and air pollution and things like that. But these are the main 2 ones, mobility and safety. In the past, these 2 main values were often in direct conflict. And most of the countermeasures we apply to improve safety meant reducing mobility, reducing exposure to risk. So for example, no right turn or right, no permissive left turn. We try to prevent mobility so we minimize interactions. But now, with these real-time safety measurements, for the first time, we can resolve this decades-old conflict between mobility and safety. I can optimize for both mobility and safety. So in summary, despite the recent success, the future of road safety is uncertain and faces many challenges. So we cannot continue to rely on the reductions that happened over the last 20 years and assume that will continue. However, there are considerable opportunities in the application of new concepts, proactive safety, vision zero, safe system approach, and many cities are doing that now. New technologies, connected and autonomous vehicles, advanced sensing and edge computing. In my opinion, this is the most exciting part, the big data that we are now generating, and we can use it to optimize the safety in real time, real-time proactive safety management. And I cannot emphasize enough the importance of research, because the research is really changing the ways we handle safety. And we are very lucky in the road safety domain, because the gap between research and practice is very narrow. So many of these techniques that I've described today are already implemented in locations in BC and many other cities. Thank you very much. We'll be happy to answer any questions.